Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
In this session, we shall study the various analytical methods that are available for estimation of evaporation. So the third approach is analytical, and hence the methods are called analytical methods. Okay. So the various analytical methods adopted for estimation of evaporation include: number one, water budget method. This is one of the most important of all. Water budget method. Third one is energy balance method, and the third one is the mass transfer method. The three methods which are available, let us study them one by one. So the first one is the water budget method. Water budgeting. Okay, this, so it's about budgeting. Budget means allocation for different heads, different volume or different amount of water is allocated, right? In that there are some allocations and there are something which is consumed. Water is some heads which consume water, so there is something called as the plus and something called as minus, expenditure. So collectively we get certain quantity. Let us say if we talk about a reservoir, like to budget water, we take the source, and one of the sources is a very big reservoir. Into the reservoir we can expect the precipitation that may occur. Into the reservoir the runoff may discharge. So these two heads, rainfall and runoff, these two we will call it as heads. These are additions to the reservoir. We say input into the reservoir. Similarly, there is some outflow from the reservoir for different uses. It can be a consumptive use or it can be a non-consumptive use. That becomes expenditure. The water is utilized for some reasons, drawn and utilized for some good purpose only, good activity. At the same time, waters are lost due to evaporation. Waters are lost due to transpiration also. So there are different heads by which waters get lost. So the sum of this, the algebraic sum of these positive quantities, that is the rainfall and the runoff, And on the other hand, we have the outflow, evaporation, transpiration also, which we'll discuss in the next topic, transpiration. All this account for the negative components of the equation. The algebraic sum will help us study the change in storage of any water body or the reservoir. So the change in storage of the reservoir is the algebraic sum of all these parameters, all these quantities. That becomes the water budget equation. In this equation, we have a small component called as evaporation. And from this equation, we find out evaporation. So that becomes not a direct approach, but it's an indirect method. Okay, so water budget is an indirect method of measuring evaporation or estimating evaporation. This this method is based on conservation of mass, law of conservation of mass. So this method is based on this law, that is law of mass conservation. So to develop the water budget equation, let us understand that if this is a reservoir, okay, this is a reservoir, then the additions to the reservoir would be in the form of precipitation or in the form of runoff. This is the addition to the waters in the reservoir or the water body. This is the water that is directly lost to the atmosphere through evaporation. Some of the waters will seep, so there is also a loss which I have not mentioned. Seepage is also a part of this water budgeting. This is also a major component to decide the change in storage of the reservoir. And then some of the waters are drawn for specific uses. This is the outflow, this is the evaporation, this is the precipitation, and this is the runoff, and this becomes the seepage as Okay, these are the components. The algebraic sum of this would help us do water budgeting and at the same time develop the water budget equation. So here what we have is the water budget equation, hence can be written as water budget equation can be written as sigma I means input, minus of sigma O stands for output, is equals to delta S. So sigma basically is the input. It can be mass input, okay, minus of output, which is again mass output, the mass of water, input, mass of water, output is equals to change in storage, and this is nothing but the water budget equation. In this we can elaborate in the equation sigma I, that is input. We can write here volume input minus volume output is equals to delta Sin. That can also be another form of the water budget equation. Here the condition is, if the densities of incoming waters and the densities of outgoing waters are same, then we can write it in terms of volume. Basically it is a mass equation. Okay, so here sigma I includes, okay, precipitation or rainfall, that is P, and also runoff into the water body, that is R, whereas the output includes the water drawn for various purposes, that we can say outflow from the water body for various consumptive purposes, and here E becomes the evaporation, and also there is one more, that is the seepage. I would mention here as loss. So same thing can be substituted here. So we get another form of the equation, that is P plus R minus outflow plus evaporation plus seepage loss, right? This is equals to change in storage. So this also is the another form of equation. So these are the gain into the water body, this is the loss, the extraction or the abstraction from the water body. Okay, you can copy this so that we can discuss the other two methods. Let us now look at the second method of evaporation measurement, analytical, that is energy balance method. This method is based on, because it is energy balance method, obviously it should be based on the law of energy conservation of energy. So this is nothing but energy in, that is the energy input to the water body, minus the energy that is lost, that is energy input minus energy output is equals to 0. Means that there is no loss of energy during the process of evaporation. Here, based on this method, based on this method, we can derive a formula that can help us calculate the evaporation rate or the evaporation loss rate as rate of evaporation in meters per second. This here, evaporation loss rate, can be written as because evaporation is mainly due to the radiation energy, right? The sunlight, the light energy. So using that energy, in the formula, we can evaluate this loss of evaporation as R by LV into rho. So here in this R, you can see here R is the radiation energy, the energy of the sun. At the same time, we should know the units for this radiation energy, that is watt per meter square. That is the unit that you have to specifically follow if you want to use this formula. This formula is unit dependent. Here, the R stands for the energy of the sun, that is the radiation energy in watt per meter square. This L, I'll write V here. This is nothing but the latent heat of vaporization. Latent heat of vaporization. The units specified are joules per kilogram, joules per kg. Whereas rho W is the density of water in kilogram per meter cube. Okay, so that is what we have. This is, let us review these terms again. R stands for the radiation energy, that is the light energy from the sun, whose units are watt per meter square. This LV in the denominator stands for the latent heat of vaporization. Now, what do we understand by latent heat of vaporization? Vaporization is nothing but evaporation. Vaporization is change in state from liquid to gaseous state. So if you have from the the intermediate physics or the school physics, we have understood this latent heat term. Latent heat is nothing but that energy that is required for change in state. Latent heat is that internal energy that is required for any change in state. From from liquid state to solid to gaseous state, there is a change in state. So this change in state is affected by we need some energy to push the liquid to the gaseous state. That energy is called as the latent heat of vaporization. Okay, and this is obviously the water density in kg per meter cube. So kindly copy. Okay, as a part of the the workbook, we shall do a small problem on this formula. That is the the energy, the formula based on energy balance method. Okay. So problem number 1. I'll read out. In a particular area, the net radiation is 200 watt per square meters and the temperature is 25 degrees centigrade. At this temperature, the latent heat of vaporization is 2441 kilojoules per kg and the density of water is 997 kg per meter cube. Neglecting sensible heat and the ground heat flux, the evaporation rate by energy balance method in millimeters per day will be how much? That's the question. Okay, so let us try to write down the data before we really solve the problem. Okay, the data given is the radiation energy R equals to 200 watt per square meters. The latent heat of vaporization is given as 2441 kilojoules per kg. So obviously this is kilojoules, so let us convert this into 2441 into 10 to the power of 3 joules per kg, which is the required unit. The density of water, rho W, is 997 kg per meter cube, and the rest of the the ground heat flux and the sensible heat are assumed 0. That means they do not contribute to this process of evaporation. So with this data, let us now find out the evaporation loss rate in millimeters per day. But this is, in meters per second. That is, this is R divided by LV into rho W. That's the formula that we have. This, if you substitute, this will give you 200 appropriate units. Before substituting in the formula, it is always advisable that you keep the data ready in the appropriate units. While we are substituting, you should be substituting only the numericals, and you should not worry about the units associated. Those units must be taken care of when you write the data. Is that clear? If you want to convert that here, it might lead to confusion, it might lead to mistakes also. So please be cautious when you substitute. Units should be clear. Okay, so the latent heat happens to be 2441 into 10 to the power of 3 joules per kg, and this is 997 kilogram per meter cube. So we have substituted the values in appropriate units, isn't it? So this, upon simplification, will give us 8.21 into 10 to the power of -8 meters per second. So the units are in meters per second. That is the evaporation rate. But as I have mentioned earlier, before we really report the answer, we look back at the question very quickly and find out what is really required. The examiner wants us to report the evaporation rate in millimeters per day. So we have to convert this meters per second into millimeters per day. So this value I will rewrite here. This is 8.21 into 10 to the power of -8. To convert meters to millimeters, we will multiply this by 1 meter is 100 centimeters and 1 meter is 1000 millimeters. So it will be 10 to the power of 3. This would be millimeters, and it is second. Okay, to convert second into days, we should know the conversion. We know that in one day we have 86,400 seconds. In a day we have 86,400 seconds. I am writing directly. Otherwise you can also do 1 day is 24 hours, 1 hour is 60 minutes, 1 minute is 60 seconds. So 24 times 60 times 60 is 86,400. It is always advisable. Please remember this unit conversion. So that 1 second, isn't it enough? That 1 second would be 1 by 86,400 in the denominator. This would be in days. We are converting meters to millimeters and second to days. 1 second would be 1 by 86,400 days. That is what we have substituted, and upon simplification you can check. The answer comes out to 7.1 millimeters per day. This is the evaporation loss for the given date. I would now request you to copy the solution. So let us now move on to the last topic in this evaporation evaluation, that is, okay, the methods to control the evaporation. So it is still evaporation. I'll write down here methods to control evaporation. Evaporation is a natural phenomenon. As long as the atmospheric conditions are favorable, we cannot stop evaporation. But keeping in view the significance or the importance of water resources in our life, when we cannot stop a particular event, we should be able to minimize, reduce, control, or prevent such events. Evaporation is one such event which cannot be, I won't say event, it's a continuous process, 24/7, because it takes place day in and day out. At the same time, it runs for the 12 months of the year. So there's nothing like evaporation stops. But then, when we cannot stop evaporation, we should be able to minimize the effect of evaporation, or we should be able to reduce the losses that occur due to this process of evaporation. Let us see now what the various methods that can be adopted to minimize the evaporation losses or to reduce the loss due to evaporation. So the methods of controlling evaporation. Controlling, basically, controlling in the right terms means reduce the losses. The first method, or you can say the various methods, such methods, include: number one, using mechanical covers. Across the world, water bodies are protected because we understand the relevance, the great importance of water resources. The awareness is there, the education is there, and the practice also should happen. So these water bodies, wherever it is practical, can be covered by various means. We can adopt domes to cover, as in the same way we cover this, this sports stadiums, where tennis is played, or probably even tomorrow you can see an indoor cricket stadium, which is, of course, the future. So we have indoor stadiums where the roof, the huge roof is covered. So there it is to prevent the rain from entering. So we can also adopt such covers, to control or to reduce the evaporation losses from the water body. So this is, of course, slightly expensive because we have to manage, we have to maintain, we have to see to it that these things are in place all the time. So this is one of the methods of reducing or controlling evaporation. Another technique, which is a bit simple also, is using what we call it as the surface floats. surface floats means, we use a lighter material and put it on the surface. When we say lighter, it floats on water. So we select those materials which are lighter than water so that they float, and when they float, they basically, or they cover the surface of the water at the surface, thus reducing the evaporation, thus controlling the evaporation. This surface floats can be what we call it as lightweight bricks. We all know that bricks can be of very lightweight, that can float on water. So such bricks can be used. They can be simply dumped into the water body so that they they cover the water at the surface, thus reducing the effect of radiation on waters. They act as a barrier, okay, against evaporation. And sometimes these wooden locks, locks of wood can also be used. We can just dump them. So if you want to, even this can serve a dual purpose. These wooden locks may also be subjected to seasoning at the same time. So there's a benefit here. It's a win-win situation that the seasoning may occur at the same time. These act as a barrier at the surface. So these are the techniques that come under the the floating material, the surface floats. The one of the popular methods is using, now this is very well commonly adopted across the world, is using chemical films. Now when I say films, you might mistake it to be a sheet. Basically it is by spraying chemicals. We spray the chemicals onto the top of water. Such chemicals should be lighter than water. They should have density lighter than water. They should not affect the palatability characteristics of water. Palatability means the appearance. They should not change the color, the taste. They should not impart bad taste and odor to water. So all this needs to be protected. Such chemicals or chemical solutions that we use for spraying over the water body, when we spray, this acts as a chemical film. You get a small film of this chemical on the top. Again, that will act as a barrier. But these chemicals need to satisfy certain conditions, as I was just mentioning. That first thing, they should be volatile. Volatile in the sense they should easily escape by themselves into the atmosphere without being detrimental to the quality of water. Secondly, they should not dissolve in water, again affecting the quality of water. Third one, they should not affect the palatability characteristics which are detrimental to the quality in terms of imparting color, imparting bad taste, imparting bad smell to the waters. All these are the requirements of such chemicals that are sprayed, but they can be really very effective. Okay, so such chemicals, these chemicals, I'll mention this, their requirements. These chemicals should be volatile. Volatile means they should easily escape without actually getting mixed with the water, right? And stay for a long time, stay for a reasonably long time. Although they are volatile, but they should have they should provide protection for a sufficient longer period. Then they shouldn't mix with water. which might, affect the quality of water. They should not impart color, bad taste and smell to water. Okay, these are the small requirements that such chemicals should satisfy before they are adopted. Now they are simply sprayed over the whole water body. That becomes a film which acts as a barrier for evaporation. The various such chemicals that might be sprayed include the most common cetyl alcohol, or the other one is the stearyl alcohol. So such chemicals can be used. These are called as evaporation suppressors or inhibitors. I'll write here. Such chemicals are called as evaporation suppressors, or they can also be called as inhibitors. But these are costly compounds, so you should keep it in mind the economy also. But if a state or a country can afford, this becomes the most effective method of controlling evaporation. Okay. Another method is by better planning of the reservoir. Better planning means we should plan the project in such a way that the water body will have what we call it as less exposed surface. So what happens is, if the surface area that is exposed to atmosphere, if it is less, then relatively the losses due to evaporation will be lesser. I mean, at least the rate of loss would be much lesser than than when the surface is more. So here also, a cup-shaped reservoir. Cup-shaped means very deep, but less surface, compared to a saucer shape. A cup-shaped reservoir and a saucer-shaped reservoir. The evaporation losses in the cup-shaped reservoir are less than that in case of a saucer-shaped reservoir, because in the saucer-shaped reservoir the exposed surface is more, hence the higher rate of evaporation. So better planning, we can say better planning, and then better operation, better reservoir operation. Now this is one of the methods that can help. This is indirect actually. What it actually means, reservoir operation means, when we are storing waters in the reservoir, it is always advised that you plan it in such a way that you utilize most of the waters before they lose out by evaporation. So when you are storing water in the reservoir, when you are planning in such a way that the incoming waters are consumed as quickly as possible, before a lot of such waters, a lot of such volumes are lost to the atmosphere through evaporation. So that is where the planning and operation can really affect in finally achieving a control on the loss due to evaporation. And one of the general methods is by planting, we can say, trees. We can plant trees around the reservoir. Now the question is, what do we get if you plant trees around the reservoir. When we plant trees, these trees act as barriers, wind barriers, isn't it? So they prevent the wind from blowing across on the surface of the reservoir. So that in a way would also help reduce the loss due to evaporation. So these are the different methods that can be better employed to control the loss due to evaporation from a water body. Okay, you can copy this. Let us now take up the second part of this topic, that is transpiration. I'll rewrite here transpiration. Okay, so transpiration. Sometimes it is also referred to as plant evaporation. So transpiration as such is not a, we can't call it as a physical process. It's basically a biological process through which the waters are lost, by the plant. Now we can say the plants sweat, just as we sweat. Plants during their metabolism also sweat. So any leaf as such, okay, any leaf as such contains what we call it as the stomata. We have a term called as, stomata. Okay, these are the, one of the components of a leaf is the stomata, and these plants, take in carbon dioxide. They absorb carbon dioxide through this, and they leave out what we call it as what and this what is water due to transpiration. So, right, so this is basically a part of a biological process wherein the plants lose water through their body. So we can say transpiration as it is the process in which the water is lost by evaporation from the body of any plant. Okay. Transpiration is basically again a loss. The loss is by physical process of evaporation, but it is not from any other part. It is from the body of the plant. So the plant loses through their leaves, waters. So that process is called as transpiration. Transpiration basically, as we all know, right, it occurs due to the metabolism. Not metabolism, we can say the process of photosynthesis. The basic process involved is the photosynthesis, right? So transpiration as such is essentially a daylight process that occurs in the day. It is essentially a daylight process, whereas evaporation occurs throughout the day and night. So transpiration takes place. This loss occurs only when there is a light, because light drives the photosynthesis, and due to photosynthesis the plant actually loses water from its body. Okay, so whereas evaporation is mainly a physical process in which even doesn't necessarily need radiation, right? It can also is driven by wind. We have already discussed the factors affecting evaporation, right? So those factors are effective 24 hours of the day. Hence, it's a day and night process. And another thing about transpiration is one small biological aspect I wish to mention here, right? As an irrigation engineer, as a civil engineer, providing irrigation to the crops, we provide waters to the crops for their metabolism, right? So any plant as such would extract the necessary amount of water or the moisture from the soil, because soil becomes the medium through which we provide water to the plant or the crops, isn't it? So the crop or maybe the plant will extract waters from the soil. Out of that water that the plant consumes to run its metabolic activity or to run the metabolism phenomena, 80% of that volume of water is lost. I wouldn't say 80%, but if you say certain amount of volume of water is consumed by the plant, out of that, if you make a ratio, the amount of water consumed actually for metabolism is 80 times less than the water that is lost by transpiration. Of course, to make it easier, I would say, the amount of water lost by transpiration is about, you can say is about 80 times, we can say 80 times, I just think 80% also, 80 times more than the water actually utilized for metabolism in the plants, or by the plants, you can say. So the actual amount consumed, metabolism here is nothing but the growth of plant. Okay, so you should know this. This is so the actual waters, when we provide waters for irrigation, so you should be aware of this fact that whatever you are providing is lost. Maximum amount of water that is provided for irrigation is lost. Partly there are a lot of losses, runoff losses, seepage losses. There are so many losses, which we'll of course discuss during you will also discuss that in irrigation subject. But whatever waters that have consumed after all these losses by the plant, in that also, hardly about 20% is actually consumed for metabolism. The remaining 80% is lost to the atmosphere by diffusion. We say diffusion. And that is routed through the body. The water comes out of the body of the plant and diffuses into the atmosphere. So if you can really see from the irrigation perspective, the actual water that is consumed by the plant is hardly a small fraction of what you actually supply. Please note this point. Okay, then the transpiration, how do you measure this? Transpiration is measured with a phytometer. Okay, so we should be able to remember, the competitive exam questions also include match the following type questions, in which you may be asked to match two choices, two lists. One list being the various processes, right? The other one is the instruments that are involved in their measurement. So let us very quickly recollect, how did we measure rainfall? It's a rain gauge, maybe recording or non-recording type. How do we measure snowfall? Right? One of the methods is also using a non-recording type rain gauge. Right? Then we coming to evaporation. How do we measure evaporation? That means the instrument used to measure evaporation is the evaporimeter or the pan evaporimeter. Okay. Similarly, transpiration. How do you measure transpiration, or which instrument do you use to measure transpiration? It is the phytometer. Phytometer is basically a small setup, okay, in which we measure the volumes of water in an enclosed container during a certain period, directly, right? The setup, the installation, and the measurement and other such associated study of transpiration we shall take up in the next session.